So gallium arsenide devices are special category of semiconductor devices. So far, we have seen a single compound devices like purely made up of silicon or germanium. But here I'm going to make combination of two different elements. I'm going to take one from third group and one from fifth group in the periodic table. Gallium arsenide, you see gallium belongs to group 3. It is going to be a P type, and arsenic is going to be group 5. It is going to be N type. So when I make these two, I get a PN junction diode. So it is gallium arsenide is a compound made of compound semiconductor. So previously silicon and germanium were individual semiconductors, but gallium arsenide is a compound semiconductor made of the two elements. Gallium is going to be having 3 valence electrons, so it is a p-type semiconductor, and combined with arsenic is going to have 5 electrons in the valence band, and so it is going to be called as n-type or donor impurity. So when you combine both, you get what is called as gallium arsenide. So this is the arrangement of atoms in gallium arsenide. You can see how the alternatively gallium and arsenic atoms are beautifully placed here. Okay, if we are going to, this is an intrinsic semiconductor. Intrinsic means it is pure. No impurity is added. If I'm going to dope it with, if I'm going to make it N-type, if I want to make this gallium arsenide N-type, means what should I do? I have to dope the silicon. The silicon will be acting as a donor impurity. And you can see when silicon is added, this silicon is going to replace your gallium atoms. So gallium has 3 valence electrons. Silicon has 4 valence electrons. So 1 electron is excess. So by having the 1 excess electron, this material possesses a huge number of vacant electrons, and thus it becomes an N-type gallium arsenide semiconductor. Is it clear? I am just replacing silicon with gallium. I am not replacing silicon with arsenic, because arsenic already has 5 valence electrons. Gallium has only 3. So if I want to increase that, I have to dope the gallium atoms with the silicon, which is going to have 4. So when you compare gallium and silicon, gallium is having 3 electrons in the valence band, silicon is having 4 electrons. The 1 electron is going to be excess. When all these excess electrons are free to move in the semiconductor, they all move when voltage is applied, constituting to what is called as current. Okay. So that is what is given here. The arrangement is given. So the gallium and arsenic atoms are alternatively positioned in the corresponding locations. This gallium arsenide requires special treatment, because if you expose this material to a high temperature, there might be problems in the surface. The bond between the gallium and arsenic atoms might break in the surface. Also, when you expose this device to very high temperature, there is a chance that the growth may be uneven. So that is the only difficulty is there. And when you fabricate or manufacture this device, you have to exercise caution in the last point. So you only group 4 elements can act as the donors or acceptors in the gallium arsenide, because already I used group 3 and group 5 here, right? So I cannot use another group 3 and group 5. So I have to use only group 4 as the doping impurity. So the covalent radius for gallium is 1.26 and for arsenic is 1.18 angstrom. Angstrom is 10 power minus 10. Okay. The angstrom unit is 10 power minus 10. So silicon atoms are larger in size than arsenic, and they tend to occupy the gallium site. Okay, so they will go and occupy the gallium site. So the silicon in gallium arsenide is used as a doping agent, and when silicon is added, your gallium arsenide becomes N-type gallium arsenide, because I am having excess number of electrons. So whenever you have excess number of electrons, it means I have added an donor impurity, or the material becomes an N-type semiconductor. Whenever I'm going to add an acceptor impurity, there is shortage of electrons. All I can say, the semiconductor becomes P-type semiconductor.